So thanks again for, if you're joining us a second time, taking the time wherever you are. It's our second in our webinar series. I'm Amy West, Program Manager for Synchro, and here with me today from Synchro is my colleague, Jason Adelars, who's our Technical Manager, and then our panelist from Seatrec, Yi Chow. So before we start, I'm going to do that quick overview. You guys have maybe seen this before, but we're let's get this in presentation mode. Just to give you a little background on why we're all here today, and what is a show and tell series. Synchro, which is comprised of this group of logos showing our marine institution partners on top and our funders there on the bottom, aims to sync the needs of a lot of marine stakeholders with some of the newly developing technology that's coming out for ocean observing. And making that connection to users doesn't always get enough attention. And so this webinar series is helping to bridge that connection, because developers like you want to design something that incorporates what users need, of course, and that's kind of harder to do than it sounds. So some of that background, in case you're hearing about Synchro for the first time, we primarily focus on, like I said, ocean observing technologies, but for ecosystem and biology monitoring. It's the tech that's still evolving, it's coming into the market, and we do this in a few ways that are listed here, these 3 ways, but it's the first one that brings us here today that I want to talk just a little bit more about, and that's helping boost access to testing and evaluation of prototypes. So we provide a no-cost access to testing and tech support with our partners, who you saw listed on that first page. And they're all here in Monterey Bay and up in British Columbia. Part of the deal of the access to testing is that we provide not only the technical support and travel support, it allows you to test and evaluate your equipment, but also we have a publicly available portal that you can provide some of your evaluation results for other potential users to access. And so on that note, by the way, we are still taking applicants on a rolling basis for this program. And Seatrec is one of our testing applicants. And after a really successful mission here in Monterey Bay, this webinar is really designed to spotlight their system so more of you know about it and you can provide feedback or ask questions. So let me stop sharing. It's just a quick reminder, there'll be about 15 minutes of presentation, and then that last bit of time will be for questions. So if you can, please put them in the Q&A. Jason's going to be facilitating. We'll get to that right after Yi's done presenting. So with that, I'd like to pass it over to Yi, who will be talking about his autonomous infinite float.
Thank you, Synchro, for organizing this webinar. Can you see my screen? Hear me okay?
Gotcha.
Thank you so much. Thank you for dialing in. Today, I'm going to introduce a new autonomous profiling float to enable fast sampling and the new sensors. We call it infinite float, infinite thermal energy. Today, we primarily focus on profiling data in the ocean. As you know, there are a lot of surface measurements from satellites, from drones. Also, we have an emerging fleet of surface autonomous vehicles powered by wind and solar and wave energy. And those are the very powerful platform provide either surface or near the surface information. Today, we are focused on more subsea data sets, which is primarily through profiling vehicles and ships. Over the last 2 decades or so, we have seen a rapid increase of these type of the sensors and then autonomous platforms, kind of they're replacing ships. And then over the last 2 decades, as you can see in the graph, the peak of the ship collected subsea data is probably in the 90s, and then you start to see a rapid decrease in data from ships, primarily because of costly operation. And also a very labor-intensive operation. I can see you can lower CTD to the ocean. Especially during COVID, you can see an interruption of the data collection by research vessels. So that's complemented by a rapid increase from autonomous robots in the ocean, primarily from systems like gliders and floats and AUVs. And today, I'm primarily focused on the autonomous profiling float. As you can see from the color-coded areas, many of the gliders and AUVs need ship report. You can see maybe a couple of hundred of those vehicles and in the water. And for autonomous profiling float, because of the autonomy, you don't need ship support, and then it's primarily expendable. You can scale up to thousands in the ocean to sustain the ocean operation. But even give you a context of those numbers, if we have, let's say, 400,000 observations per year, and if you divide it per day basis, you can see you only have one data point for the size of the ocean of California. So you can imagine it's really challenging to tell how ocean changes from day to day, from hour to hours. And that certainly we need not only doubling the observation in the last decade, we probably will need a 10-time or even 100-time increase as we build the blue economy, require data to train the AI smart algorithm to make better decisions. To sustain 4,000 Argo float, probably one of the most successful international programs. As you can see, profiling float is primarily changing its buoyancy, moving up and down. Typical Argo float park at 1,000 meters for about 9 days, and they surface to collect a profile data from conductivity sensor to measure temperature salinity. And then you can tell many of these are float lasting about 3 to 5 years, just because the battery capacity to change the buoyancy in the float. So if you can do the math, you have 4,000 float, you make a couple of hundred profiles every 10 days, basically require almost 1,000 of these float to be deployed every year. And that's certainly put a cost in a very high demands, and also the ship time to continue to deploy this float over the entire globe. As you can tell, because the figures on the lower left, the 4,000 float, because of the success of the Argo platforms, the community has been requesting more and more sensors to be added to the fleet, not only go deeper, like deep Argo, you're going to have increasing amount of Argo floats carry biogeochemical sensors, we call it BGC Argo, to collect more than temperature salinity data sets. If you go through the list of the climate variables, the essential variables established to community, we have a long list of variables to be measured, from physical properties to biogeochemistry, all the way to the marine ecosystem, to the plankton population. We want to know the velocity so we can estimate the mixing parameterization, validate our models, and a number of different biogeochemical parameters, the Argo platforms. Now, not only the Argo can monitor climate, there's increasing demand to profile faster. Their community already started to reprogram some of the Argo float, for example, in the Gulf of Mexico, to profile faster, more frequent than 10 days, to monitor the mesoscale processes, and then to provide the data for hurricane prediction. Anticipating this is a very big hurricane season, certainly have an important need to deliver this data. So how do we profile more frequently and then carry more and more sensors using this type of platforms? And as I mentioned earlier, is a limited capacity with the battery powers. So you have a compromise between more frequent profiling, new sensors, and also how long you're going to sustain this kind of the fleet of 4,000 floats. So the community has been thinking about this problem over the last many decades, since Henry Stommel published his first seminal paper in 1989. And he envisioned this Argo type of float, and it could be sustainably powered by the ocean temperature stratification. As you know, there's an infinite thermal energy associated with the thermal gradient. Over 70% of the ocean have this kind of stratification in the ocean. Potentially that infinite thermal energy can be converted to electricity and then to charge the battery of the profiling float. Doug Webb is the lead engineer from Henry Stormway Woods Hole, even filed a patent decades ago, and to use wax-like materials to changing the buoyancy for the profiling float. I believe Doug eventually built a couple of these for testing, but never been pushing into 100% sustainable for the population, for the Argo operation. So there's limitation. Doug Webb has been experiencing the buoyancy. You cannot store the buoyancy. You have to use them all the time. So sensors and have to carry their own batteries and then have limited lifetime. So you can imagine it's really costly to lose a float, and then a lot of the valuable sensors will be lost. Certainly not scalable. Once you get limited battery involved, it's also not sustainable. We lost about 1,000 float in the ocean every year. So we kind of coming along, standing on the shoulder of the giant here, came about 2 decades later. So I did start to develop this technology collaboration with Ross Davis at Scripps and UCSD, and then to push one step further, not only use wax material to change the volume of the device, but also we start to packaging this material in the profiling float so that we can generate electricity. So when this material melted from solid to liquid, when it's come to the surface into the warm water, so that material kind of turn the thermal difference into a volume expansion. So that expansion imply a kinetic energy that can be harvested into electricity, recharge the battery. So we developed the prototype, filed the patent 2011, more than 10 years ago, demonstrate it is possible to completely power this type of profiling float by the ocean clean renewable energy. So that's kind of start my startup journey to build this product. And then we spin off from Caltech, JPL, where we developed this technology funded by Office of Naval Research back in 2016. Has been really fortunate to have those visionary sponsors like the Thiel Foundation wrote the first check for us to start this commercialization journey, followed by the Schmidt Marine technology partners continue to fund us to reduce the risk. And then with government support, SBIRs and Office of Naval Research and NOAA, and to help us to launch our product last year. And then we start to not only targeting Argo type of oceanography application, we also envision our profiling float can deliver data for a number of different new areas, such as hurricane prediction, weather prediction, soundscape monitoring, and seabed mapping. I mentioned a few results for each of the 3 use cases, and an open door for additional sensors, ideas from you all to help us to apply this platform for other application areas we never thought about. Just to give you an example of the Infinity Float we demonstrated recently, early this year. It's the first subsea robot. We have been surfacing more than 700 profiles every 6 hours. So for the first time, we're able to deliver this 6-hour frequent sampled profiling data completely powered by the ocean. You can see the CTD profile showing in that insert here. Each dot in this spaghetti diagram showing the surface position every 6 hours. We launch off the coast of Kona, have been traveled pretty far out in the ocean. You can see some of these trajectories like mesoscale eddies in the ocean being drifted, circling around. And we measured the energy we harvested, about 10 kilojoules, or about 3 watt hours every dive. And with the CTD, we only use half of those energy. So there's extra energy we could save to power other sensors and then store them and then to do other missions. Just to give you an idea what the 6-hourly profiling data look like, you can do spectral analysis. You can see a lot of different frequencies and then fast changes in the ocean coming from the diurnal cycle, the synoptic associated the weather fluctuation. So during this 6 months mission, and then we see a variety of different time scales. You'll see up and down the mix layer. And then many of these features is difficult to resolve with Argo type of 10-day profiling. So it's really revealing to see the multiple time scales in the ocean involved. we are in the position to deploy a new float in the Gulf of Mexico, hopefully in the coming months or so. In the middle of the hurricane season, we anticipated it's a heavy active hurricane season this year. And then just to show you the example on the right-hand side, how much progress we need to make in order to improve the hurricane forecast. Last year, the Hurricane Otis in the Eastern Pacific, you can see all the models in the color graph doesn't really show a forecast of the hurricanes and the tropical storms. And this storm surprised to all the meteorologists and then intensify into a Category 5 hurricane. It's just within a day before landfall. So there's an urgent demand to have data from the air, from the surface, from the subsea to improve this kind of model forecast so we can protect lives and then the blue economy. Another use case I want to highlight is using passive acoustic hydrophones, and I highlighted here is a non-directional hydrophone we have tested. Also, we're in the process of, with NOAA funding, to test a directional hydrophone in the coming year. Looking at different frequencies, you can use this type of information to derive both natural sound, man-made sound, marine mammals, a variety of different applications, from how do you avoid ship strike of whales when they, during the shipping route, offshore energy, wind farm, for example. How do you assess the impact of marine mammals to fishery, not to mention defense applications, and how do you develop the 100% awareness subsea so you can inform the commanders and then make better decisions. So a variety of different applications. So we did a first validation in the Monterey Bay, deploy our float. You see it in the size a little bit bigger than the Argo float, still deployed by 2 people on the small boats. So we deploy on top of the cable power hydrophone. So now you can compare hydrophone on the autonomous system against the cable power hydrophones in detecting blue whales and fin whales. So for the first time, we're able to demonstrate float is really good platform. When we park at 400 meters, in this case, we can detect essentially the same information you detected from these $10 million cables, and only a few places you can afford to have them. This is the most recent deployment. This is a part of the Synchro project. Thanks to Jason, organized this both support and deploy this 10-day mission, and then we can park at a certain depths. And then we also, another feature of the float, we carry a Linux computer. Our collaborator enabled postgraduate school able to load the Python code before we deploy, and then do the data processing essentially on board to reduce the data size in order to do satellite transmission in real time. So we surface every 6 hours. So I will stop talking for a few seconds. Hopefully you are here. In this mission, we detect humpback whales. Let me know if you hear it. Okay, so final example I want to show is we, in collaboration with scientist Larry Mayer from University of New Hampshire, David Sandwell from Scripps, and we are in the process of developing another sensor, collaborating with 2 innovative companies making sonars, and Innomar in Germany, Airmar in the US, developed this customized parametric sonar so we can do a single beam seabed mapping. So imagine all the 4,000 Argo float carry echosounder. So we should be able to map the seabed 100% by the end of the decade, which is a goal of the seabed 2030 with the current surface vehicles and ships mapping, the conventional mapping techniques. We anticipate we only map about 50% of the seabed, only half the goal of the seabed 2030. With the conventional methods, take 50 ships, 2 gigatons of CO2 emission, about $3 billion to map them. So we hope to deploy this echosounder in the profiling float to demonstrate this is the powerful platforms. The last slide I want to show is in addition to the couple of sensors I showed you, the conductivity, measure temperature, salinity, hydrophone, measure soundscape, echo sounder mapping seabed. We are in the process, thanks to synchro support, we're in the process of procuring a UVP sensor, underwater vision profiler, to do imaging as we profile. We can profile particles and zooplankton. Working with Nortec, we plan to deploy ADCP so we can mapping the velocity and profile the share of the velocity to estimate mixing, validate models. And in collaboration with scientists and the Kongsberg team, we're also thinking about potential echo sounder we can looking on the side to mapping zooplankton profiles and then in the future. So looking at new applications and new ideas to help us to think about potential applications, and we can discover more of the ocean. I will stop here and take your questions. Thank you very much.
Oh, thank you so much, Yi. I was thinking about storm chasers going into the middle of a storm with planes. Now we can just send a float down and hide from it. So everyone, we would love for you to pose any questions or ideas, anything you want in the Q&A. Simultaneously, we're going to be launching a poll. There are 3 questions. This helps Yi, so please scroll, and fill that out during the next 5-6 minutes. And anyone want to, or if you want to speak, you can raise your hand. But yeah, please pose any questions you might have or comments.
I think while they're doing that, I had one question is typically, we deploy a float, it's at the will of the ocean, it's just going to travel with the currents. And I think maybe there's some really great use cases to be able to do some station keeping on a position. Are you trying to discover some functions like that?
Yeah, that's a great question. I think Argo community already thinking about in that direction, using model forecast to optimize the parking depth so we can let the float to be drifted in the desirable direction. So we are envisioning one of these ADCP sensors will help us to profile velocity, so that help us to optimize the float drifting trajectories, either through the ADCP data itself or simulating into forecasting models, so we can park the float at red depths, and then eventually the float will be either keeping station or be drifted in the desirable direction. So having velocity is a critical information to control, kind of steer our float in some way in a more passive manner without using propellers and gliders.
That's great. And how about, so I know a lot of these newer sensors that we're talking about, these ocean, the UVP and echo sounders are super data dense. Can you talk a little bit more about how, you can condense that data so it can be sent over satellite?
Yeah, that's a great question that responds to that kind of demands. Our float is adding a second computing board, is also running a Linux operating system, as I mentioned. Specifically, it's a passive acoustic hydrophone. You can collect 10 gigabytes of data per day, and then it's just impossible to send to a limited bandwidth Iridium satellite today. So our Linux computer does envision allow users to load their programming program is to process the data, building certain detectors. Oh, I hear blue whales, and then send me the spectrogram, send me the EOF coefficient, so you can compress the data for our defense customers, and they can encrypt data to further protect the information. So there's a number of different ways to use our Linux computing platform, so you can do the cloud computing essentially in the water on our float without transmit to the cloud.
Yeah, no, that's super useful. We've got one question here from Danielle. How did you work with Synchro to forward your infinite float mission?
That's a good question. We really benefit from the Synchro program. For example, this 10-day mission, I highlighted it, collaborating Naval Postgraduate School, really facilitated by the Synchro. They provide the vessel support. And because the Monterey float doesn't have a propeller, And essentially, this is the first time we have a vessel standing by in case the float is drifting away and outside the range of the vessel we can afford. So they provide the travel support, provide the ship support, also the captain and Jason and his team available essentially 24/7 to recover the float wherever is necessary. Fortunately, the float kind of behave very nicely in the Monterey Bay, so we don't have to mobilize our effort at midnight, but the Synchro does provide that role to do that recovering operation in case the float get drifted very fast offshore.
Yeah, plus we were able to track it real time with our ODSS tool. And that was, we were able to, see it every time it came to the surface, we got a position, and that was very useful. Let's see, I've got a couple more questions. I'm just gonna start on how the infinite float differs from other passive monitoring devices. And can you control the pathway of data collection? And then can you control how deep and how fast the floats come to the surface?
Yeah, we can control the parking depths. You can park, the user select the mission profile. You can park 350-meter today for 6 hours, and then 450 for 8 hours tomorrow. And then you can certainly profile those. Our typical vertical speed is about 10 centimeter per second, like most of the Argo type of float, between 5 to 10 centimeter per second speed. Certainly user have ability to accelerate that speed. We tested 20 centimeters per second, 30 centimeter per second. Of course, you consume more battery power, and then going faster is not even linear. So the advantage of our float is you have a lot of control. So you can do the mission control, you can do the speed control, and you can watch the energy battery level. So then the battery run low, you can set to energy harvesting mode, and then they can recharge the battery and then give you a new mission opportunity.
So as a user, does the float come with a dashboard that the user can kind of communicate and send additional commands and make some change parameters to the mission?
It's coming. It's not tomorrow. Right now, we are a hardware company. We sell float hardware. We provide the standard user support, and then we have increasing demand from the customer, like this question. So we are providing certain services and then helping potentially the dashboard. But right now, basically, you have to email support@seatrec.com, or our user support will help you. But in the future, I certainly can envision a dashboard, and then you can go log in seatrec.com, you control your float, you control your speed, and then you can optimize your mission. And then if you click the button, our engineer can come in to help you have a Zoom call or something.
Okay. Another question we have is appreciating the additional complications of having floats closer to shore. Is there a way, to what degree can this system deliver, a better vision for more of a coastal zone measurements?
That's a great question. Argo already lay out the priority to go in the shallow water. Most of the float today is not designed to be operating in the coastal areas, and there has been a number of effort to, like Monterey, for example, develop a float you can park on the bottom. I think the NKE float from France also testing their parking capabilities. So essentially, you can park a float at the bottom if you want to avoid the drifting, stay more time in the coastal ocean. We envision our float will be more smart, knowing the bathymetry. You don't have to hit the bottom, so you can profile according to the depth you have. Potentially, you can even install one of the echo sounder we are developing. So essentially, you can tell it's 350-meter now, and park it or stop my profiling at 300 meters. And then next day, you're going to say 250 meters, and they're going to stop at 200. So that kind of thing is potentially coming in the future, knowing the bathymetry, measure the bathymetry, and then control the float more dynamically. So that's really allow us to extend the deep water profiling float into coastal applications.
And similarly, the more near shore, you have different water densities than like way offshore. Is the buoyancy changes able to kind of account for that change in water density?
Yeah, that's the advantage of a float company coming late. So we design our buoyancy engine almost 3 times bigger than typically the Argo type of float. You don't have to ballast to the precise ounce of the materials in the float. So we can do a lot of the dynamic adjusting of the buoyancy and also allow us to accommodate different water density regimes and freshwater lenses and then to surface as needed.
Thank you, Yi. That was fantastic. I'm guessing everyone else out there needs one. That's why we're all so quiet. So contact Yi. But thank you everyone for attending. We're gonna post this recording as well to share with others on our YouTube. You'll get a reminder email about it. But I just want to thank everyone for the questions and Yi for his presentation and for taking a half hour out of your day. And we'll do this again probably in another month. So thanks everyone.
Thank you very much.
Bye.
Bye.